All right, the learning targets. I can find rational zeros using synthetic division, and I can find all real zeros within a boundary using synthetic division. Notice that both actually end up using synthetic division, although for rational zeros, we can go another path. All right. So, the rational zero theorem tells us that all candidates for our rational zeros can be taken from the following expression. All right. I can create a fraction and take the factors of my last term of my polynomial and put them over my factors of my first term. And that should simplify to give me all possible rational zeros. All right? So, let's try this out. This is my last term. Factors of 1, well, that's just 1 times 1. All right? So, I'm going to put, the factors of 1 are 1, but it can be positive or negative. So for every factor we list, we're going to put a plus or minus next to it. All right? If that's my last term, check. Okay, over the factors of my first term. Here's my first term. That is a coefficient of 1. So again, we're just looking at the number, and that's, again, 1 times 1. So it's only one, number 1, plus or minus. So all possible. It doesn't mean they have to be here. Just if they are, they would be from this group. Okay? All possible rational zeros come from this expression. So I can have a positive 1 over a positive 1. Okay? I can have a negative 1 over a negative 1. I can have a positive 1 over a negative 1. Or I could have a negative 1 over a positive 1. So ultimately, these two are just giving me a positive 1. And if I simplify these, it would give me a negative 1. So really, if there are any rational zeros for this expression, they would be either 1 or negative 1. If there are any rational at all. Maybe none of the roots are rational, and that could be the case. So how do we check to see if these work? Well, if these are the roots, if they're the x-intercepts, if these right here are the zeros, okay, we don't know. If they're the zeros, that means if I plug them into my polynomial for my x's, it should equal 0. All right? So let's try this. Right now we have f of x equals x cubed minus 3x squared plus 1. All right? And I'm going to see if f of 1 equals 0 and if f of negative 1 equals 0. If either of these are 0, then those are rational roots. If not, then it has no rational roots. Okay? So, I've got 1 cubed, again, I'm just putting them in for my x's, minus 3 times 1 squared plus 1. Well, that's 1 minus 3 plus 1. That's negative 1. So that is not a root. No. All right? This next one, I'm just going to put a negative 1 in for all my x's. Because negative 1 squared plus 1 equals negative 1 minus 3 plus 1. That's negative 3. This is not a root either. All the roots, my problem here, for this polynomial are either imaginary or irrational. And if I look at the graph, well, here's where 1 is, negative 1. Here's where positive 1 is. These are not rational roots right here. It does have the 3 roots, but they are not rational. All right? So our theorem holds true. All right, here's another example. Find rational roots algebraically of f of x equals 3x cubed plus 4x squared minus 5x minus 2. So what are the possible rational roots? All right? Well, I take the factors of my last term. The only thing that multiplies me 2 is 1 times 2. So I take 1 and 2, and they are on the top. Again, plus and minus, right? What are the possible rational roots? Well, it's the factors of the last term over the factors of the first term. And the only way we get to 3 is 1 times 3. 1, 3. So what are the possible roots? Well, I could have positive 1 over a positive 1. And I can have a negative 1 over a negative 1. So I guess I can either have plus or minus 1, because that's 1 over 1. Then I could have 2 on top and 1 on the bottom. That's 2, and it could be plus or minus. Okay. I can have 1 on top and 3 on the bottom. So it would be 1/3. Again, it's plus or minus. Or I could have a 1 on top, or 2 on top, and a 3 on the bottom. So I have 2/3 plus or minus. Now this question isn't asking me to figure out what the roots actually are. These are just the possibilities. Now I have to go through and test these. And if I look at my graph, right here, this crosses right at a positive 1. So positive 1 is one of my answers. Okay? This right here crosses at a negative 2. So a negative 2 is one of my answers. And this right here is a negative 1/3. So negative 1/3. Remember, this is a list of possibilities. Okay? This is doesn't mean all of them are roots. That means if there are irrational roots, they will be one of these. Okay. Real zeros within boundaries. Okay, the upper and lower bound test for real zeros. Okay. If polynomial's lead term is positive, that's important. And this lead term is positive. Okay? And using synthetic division by the upper bound will result in all positive or zero values. Okay? And if we use synthetic division by lower bound, the result will be in alternating values, which means it'll be a positive and a negative and a positive and a negative. So, what is this upper and lower bound? Well, let's look at our problem here. Let's prove that all real zeros of this polynomial, f of x given, must lie in the interval between negative 2 and 5. This is my lower bound, and this is my upper bound. That is the actual interval. Everything from the low end of negative 2 to the high end of positive 5. That's the interval. They want to make sure that all real roots are between them. And we're going to do this using synthetic division. So according to my rule, if I use my upper bound, my answer will be all positive. Maybe 0, but all positive. All right? So, if my upper bound is at 5, and when I use synthetic division, I don't use the 5. I would use the binomial the 5 came from, meaning I would have to have x minus 5 and solve for that to get x equals 5. All right? So the minus 5 is what I'm actually going to use for my synthetic division. Okay? And that's going to go into my 2, and negative 7, and negative 8, my 14, and my 8. Again, for synthetic division, I just want the coefficients. All right? And how do we do this? Drop the first one. 2. Negative 5 times 2 is negative 10, and I just subtract all my products. That will give me a positive 3. Negative 5 times 3 is negative 15. If I subtract that, will give me a positive 7. Negative 5 times 7 is negative 35. If I subtract that, that will give me 49. And negative 5 times 49 is 235 negative. If I subtract that, that will give me 243. Are these all positive or 0? Yes, they are. Positive, 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 positive. That means this is the upper bound. We're good. Upper bound works. It checks. Now I do the same thing for my lower bound. If my lower bound is x equals negative 2, well, through division, I'm going to divide in the parenthesis or factor that negative 2 came from. I would have to have x plus 2 and t-bone and solve to get x equals negative 2. So my positive 2 is what I'm putting into my synthetic division problem. Using the same numbers. 2, negative 7, negative 8, 14, and 8. I'm going to drop the 2. 2 times 2 is 4. I subtract it, that's negative 11. 2 times negative 11? Negative 22. I subtract it. I get positive 22 minus 8, 14. 2 times 14, 28. I subtract them, so it'll be negative 14. 2 times negative 14, negative 28. If I subtract them, it's positive 36. Right, let's see. Positive, negative, positive, negative, positive. Is it alternating between positive and negative? Absolutely. Which means this works out, this is our lower bound, and all of my real roots should be in between this interval. So if I were to graph it, this is graphed from negative 2 to 5. It should have at most 4 roots, 4 real roots, not rational, real, which means it actually touch the x-axis. 1, 2, 3, 4. 4 roots, all between the interval negative 2 and 5, and they work.